Thank you very much, Nadav, for the invitation. It's a pleasure to be here in this really beautiful establishment where you really feel the weight of time and you get inspired by it. So, indeed, I will be presenting, I will be talking about scattering amplitudes and Feynman integrals today. And I am at City University of London, so local, at least for the time being. And this is my email address where you're welcome to write to me if you have any questions after the lecture. This is also where my office is. And of course, I'll be sticking around after the lectures and we can chat, but you're also welcome to stop by there. And these are mostly the material I will be based on and drawing from. The first four, so they're all archive, so they're publicly available for you to access. And the first four I had already pointed also were already included in the email you received. And these are part of the SageX review. So SageX was a collaboration European Union, the European Union, including many institutions, yes, and which was also headquartered here, in fact, in the UK at Queen Mary. And these are also a few more references for you. This is a good book that is publicly available for scattering amplitudes. This is also a good lectures from Tassi. Some a bit old, but still they contain lots of useful information. Sorry, this is, I think, the book that is publicly available. This is also a book on Feynman integrals, and this one I forget. Hi there. Sorry, these four were already included. Okay, yes. So it was mostly be these four, but these are additional resources for you to have. And the broad outline of all the courses that we will cover today goes like this. We will start with some motivation why scattering and Feynman integrals are interesting, yes, a topic to focus on. And at the expense of boring you, I wasn't sure what the level would be, so I thought I would start by reviewing some basic facts about quantum field theory, the basic framework we're describing most interactions in nature, but also scattering amplitudes and Feynman integrals draw from. And then I will introduce some very convenient variables, spin or helicity variables that simplify determining these quantities and how to further write them down in simpler pieces. So most likely we'll go up to here today and continue. So this is roughly also the lectures that we will cover, but not quite. Then the next lecture, we will start with the first approximation for scattering amplitudes of Feynman integrals, some three levels, so-called three-level methods. That's where we start. This is where we are still at the realm of the classical world, but we we start, let's say, easily, and we see how we can devise of more on more efficient methods for computing amplitudes that do away with, in fact, Feynman integrals and diagrams and rely on some core properties and mathematical beauty. And this is the BCW recursion. Then in the third lecture, we will go to loop level. We will go to where really quantum effects kick in. And we will, in this case, look about the building blocks or constituents of scattering amplitudes, Feynman integrals, just to simplify the discussion. And we will look at their function spaces, the types of functions that describe them, so-called polylogarithms, their generalizations, and also where they develop singularities as values of the external kinematics. And if time permits, which I doubt it, but let's be optimistic, I can also dive in like more advanced topics related to bootstrap for amplitudes, or the mathematical structure of cluster algebras and how they appear. So this is the the big picture. Are there any questions at this stage? All right. If not, let's begin. Maybe I can start here. I was warned that I should not be using this bit too much, but this is, yeah, for different reasons, as you see. But let's very briefly say, why are we studying what we are studying? Uh, so motivation. And so we know that scattering amplitudes, so I will describe like this. You don't see from there. It's all good? So they are theoretical input for collider and more recently also gravitational wave physics. So we have the LHC, we have a big ring under CERN, and we have particles that accelerate almost at the speed of light, protons and antiprotons, and they smash into each other. Sorry? Protons and protons. I said antiprotons, sorry, protons and protons. Proton-proton collided, very good. And they smash into each other, and then we watch what comes out. And for example, we can have some gluons that collide, and then we can't see at what's happening at the quantum level, and out might come another gluon, and then also maybe a Higgs particle, such the last missing puzzle of the standard model that was discovered about 10 years ago. And then more recently, so this is the at the framework of quantum field theory that describes both quantum mechanics and special relativity together. More recently, and this has been known that to describe all interactions in nature except, let's say, consistently gravity. But more recently, we have understood that the same technology can also be applied to gravitational wave physics. And in particular, we have black holes that are orbiting around each other. And they emit gravitational waves, which we detect by LISA, by ground experiments here. It turns out that even though our framework, quantum field theory, is mostly designed to describe quantum phenomena, nevertheless, the path integral, some of the basic concepts of quantum field theory, are very good in organizing a perturbative expansion, in solving problems like approximately order by order in some parameter. And in this case, we have the Newton's constant, the gravitational constant being small, and also velocity being small. And so we can organize how to, approximately solve the Einstein equations little by little with knowledge and technology from quantum field theory. This is like very brief motivation. And of course, these are things that maybe you have all seen at some level during your masters. And so you might ask, okay, they appear, they play a role with respect to experiments, but why do we teach them here? these are known things for a long time. But the thing is that while conceptual foundation is clear and was developed for decades, then the complexity of intermediate steps grows extremely fast. So even though the concepts are there, when we really try to make contact with experiment and provide some theoretical input, we run into walls, we run into serious challenges. And this happens even if end result is simple, this intermediate complexity. And I will give an example of a formula which we will hopefully understand today towards the end of the lecture. But this is the so-called three-level MHV amplitude, maximal helicity violating amplitude of n gluons. And this is first of all an all n result. So it doesn't matter how many gluons the particles of the strong interactions are participating. Oops. But in the end, you get a beautiful formula that fits even in this little piece of blackboard. So how can this be? And so in order to overcome these obstacles, overcoming challenges, to even get here or devise more efficient ways to get there that circumvent this complexity, require some revolutionary ideas over the years, and also in rich interplay with mathematics. So if you wish, this field of research has the benefit of both serving physics in the sense of providing input for experiments and also making touch with some very beautiful mathematical structures and exploiting them to actually arrive at the final answers. So that's, and mathematics very broadly, one can think about algebraic geometry, number theory, combinatorics, all branches of mathematics play a role, and that's why also there have been very interesting synergies between physicists and mathematicians addressing these issues. Questions? If not, then let's go on with a brief overview of quantum field theory, just to set the stage and also set up our notations for later. So 1.2, so that was 1.1, 1.2, QFT review. Why do we need quantum field theory in the first place? So we have a very well established, let's start by answering this question and refreshing our memory. We have a very well established framework for quantum mechanics, developed even earlier at the start of the 20th century. Why do we need quantum field theory? Why isn't that quantum mechanics is not enough? Yes, let's say why is it that relativistic quantum mechanics is not enough? You want locality, yes. Sorry? Very good, exactly. So if you have quantum mechanics and special relativity, you know that you have varying number of particles or degrees of freedom. And this quantum mechanics, relativistic or other, yes, or otherwise, simply cannot do. It becomes inconsistent. The number of particles is essentially fixed in quantum mechanics. So this is why we need quantum field theory, because when you combine quantum mechanics and special relativity, you know that particles will eventually be created from like if lots of energy are accumulated, or will be annihilated in pairs. It's a simple consequence of bringing these two basic principles together. So this is why what QFT can do or quantum mechanics cannot do. QM cannot do that. So that's why we need quantum field theory in the first place. And then, okay, then we go from classical particles to fields where you have some Lagrangian L and you make it a Lagrangian density. So equals T minus U. You go to a density L. So L is the integral over the whole space-time of curly L is the integral of usual L, standard L. And then similarly for the action, which is just, sorry, the integral of the Lagrangian. And yes, this becomes, in this case, exactly dt d, let's say we are in d dimensions in total, d minus 1x L. So this is relatively straightforward from going from particles to fields, let's say quantum or otherwise. And then we also have, you have studied in your quantum mechanics courses first free relativistic fields. For example, one starts with scalars and one studies, let's see, lambda Klein-Gordon, d mu phi minus f squared phi squared. And then this has an equation of motion that is the Klein-Gordon equation. And here we have our conventions that, let me, if I use green color, is it visible? Tell me. So if I write that eta nu is plus, minus, 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 is it visible? Good. All right. So these are my conventions. And so hopefully, yes, I don't have to write everything down, but T mu is T by dx mu, and so on. Do ask if, yes, you would like any clarifications, but this was just to set the stage for some of the conventions, as we said. And then we also have Dirac. We have studied, let's say, I'm refreshing what's been covered, let's say, in the standard QFT course. We have Dirac fermions that have some action Dirac equals psi bar I gamma mu d mu minus m psi, so bilinear in psi bar, where psi bar is psi dagger gamma 0, and these are the Pauli matrix, sorry, the Dirac matrices. So for the let's say Pauli matrices, so generalizations of the usual Pauli matrices that you have seen in SU2. These are in 3 dimensions, is 4D generalizations. And again, the EOM look like d slash minus m psi equals 0, where this is again equals new dB, again for the notation that we use. So far so good. All right, just to get to know each other with some formulas we have hopefully seen, and therefore you don't feel frightened about, you feel comfortable, relatively comfortable. Let's start from our comfort zone. And then finally, we also have the third player in the game, our S or U, SUN or SUN gauge fields, or non-abelian, or yes, gauge fields that can be abelian or non-abelian, and those have a Lagrangian density that is where this here, so field, this is the field strength of the gauge field. So F mu nu equals D mu alpha nu minus D mu alpha nu minus IG, let me write on this line, minus IG A nu, where this is the coupling. So this is the coupling, the gauge theory coupling, and this is what appeared, for example, in the formula for gluons that I had before, just to be explicit about where all, let's say, our yes, players of the game are. And in this case, you can write the equations of motion as d nu f mu nu, where yes, d is the usual derivative. This is the covariant derivative, so it also includes the coupling in it. And this is a usual commutator, also a mu dot a nu minus a mu dot a mu. And why is this thing non-zero? Because the gauge field is a matrix. Is a matrix, so you can write it as a nu a ta sum over a where these are the generators, SUN generators in the adjoint representation of the gauge group. So this okay. If has everyone encountered this already? Sure. Okay. So you know what I'm talking about. And okay, if we are thinking about the U1 case, then of course this thing is a simple number. This is zero. So this is quantum electrodynamics. This is just the electric field. So who would like to go faster? Is anyone who would like to go faster? Yes, I see someone who would like to go faster. Does anyone like to go faster? Is this too pedantic? No. Okay. I see also some more experienced people that say it's good, so I won't go faster. And then, okay, then let's. Okay, so we studied in our QFT course the free fields. And then those were still classical, we quantized them. And these parallels passage from classical to quantum mechanics, in the sense that you have some Poisson bracket, P x equals goes to 1, so Poisson bracket. So this I will not define, but do ask if you want to recall it. And then what happens is that if you go to the quantum world, then you replace this with a commutator, and you put also an h bar in it. So now P and X are operators. They are no longer just classical quantities. So, or we can put this on the other side, and this is, yes, the fact that P and X as operators don't commute. This is conceptually how we can easily transfer from classical to quantum mechanics. And so observables are operators when we do this. And so similarly for fields, we have something like the conjugate momentum pi t and x, and then phi. I'm thinking of the scalar field just as a prototype of field on the simplest case, and then this becomes again some commutation relation between the same quantities. So I will not write this here. Well, this is delta x, so this is yes. Well, let me write it here on the right hand side, equals delta. Sorry, this should be x and y. So it's equal time commutation relations. Yes. So we look at the operators at the same time, and this should be x minus y. So just the spatial part. So again, where okay, this is defined from the Lagrangian, the conjugate momentum. So I will not go into this, but do interrupt or ask questions, and let's make this as interactive as possible. Okay, and then so So from let's see. So going through this passage means that the solution, so then solution of let's say of Klein-Gordon equation can be written as phi of x equals the three-dimensional momentum. Okay, there are some factors of pi cubed. There is some measure that depends on the energy of the particle. And then, okay, I continue here. Alpha dagger, so A dagger, that depends on the momentum of the particle, E, an exponential E to the energy times time muon minus P dot X, the spatial part, and then also with plus A, P, yes, different sign. Okay, so what have I written over here? I have essentially solved the Klein-Gordon equation that I showed you before by some plane wave ansatz, or if you wish, I've gone to the Fourier space to solve the equation. So I plug in some plane wave solution, and I find that the energy squared minus the momentum squared should equal the mass of the particle. So in this case, E is square root vector P squared plus M squared. And so this is the classical solution. And then when I go to the quantum world, these coefficients that were simply just numbers now become operators. And therefore, we can construct states acting with these operators. You have the vacuum, then you have a dagger P1 vacuum. This is a one particle state, so vacuum, particle state, and so on. So this is, in a nutshell, how we have now varying numbers of particles, evidently. We can construct as many particles as we want. That's why we needed QFT in the first place. So, analogously, I will not repeat, analogously, we can also do it for the fermions and the scalar field, but now these are multi-component. And equations, so differentials, equations, and therefore also solutions. Who remembers how many components the Dirac spinor has? 4. Very good, in 4 dimensions. And can some explain roughly why it is 4? Does one remember? That's the mathematical way, but if you want my way, so does the Dirac fermion describe, let's say, so is, um, what is the antiparticle of the Dirac fermion? Or, sorry. So Dirac fermions describe both fermions and antifermions, so both particles and antiparticles. So And roughly speaking, okay, we are talking about spin half particles. So if you want, you roughly have spin up and spin down for a like positive energy particle or a fermion, and then spin up, spin down roughly also for the antiparticle. And particles and antiparticles are distinguished by positive and negative energy solutions. So like these solutions, the fact that you have many components, they are because, let's say, particles for psi, you have particles describes and antiparticles that are different from each other. So the antiparticle is not the same as the particle. They are two different species. And also spin information. So roughly spin up, spin down. So spin half. So this is how you get 4 components. And so yes, so therefore you will have the same type of general solution here, but you will also have some spinors, so some constant spinors combined with them. So let's say in this case you take the Dirac equation, so um, so again, plane wave solutions, solution which can be either u dot e to the IPX. I'm not separating now the energy and the time component, or v e to the minus IPX. So positive and negative energy. And so if you use if you plug this in the Dirac equation, you see that okay, you still need the dispersion relation that E is plus or minus m squared plus p squared. You still need this to get a solution in the form of a plane wave, and you also need that these spinors also obey the momentum space version of the Dirac equation. So U, so this depends on P, and then similarly equals 0, and similarly P slash plus M V of P equals 0. So you have some additional constraints that your objects, your spinors, need to obey. And this would come, let's say, roughly multiplying each of the exponentials here. All right? So if we're talking about particles with spin, we have to somehow describe the spin degrees of freedom. And this is how we describe them with these spinors, positive and energy spinors or polarizations. And similarly for the gauge field, and so for gauge field, again, similarly for a nu, it's a 4 vector. One would expect 4 different components, or let's say physical solutions to the equation. However, how much do we have? Who remembers? 2. Very good. And why is that? Or who said it? Very good. The 2 polarizations, yes. One can motivate it from the so think the classical electromagnetic field. You know that if you have the the direction of the propagation of the wave, then you have two polarizations, the electric and the magnetic field, to be like two vectors, in this case three-dimensional vectors, that are perpendicular to it, the two perpendicular directions of the electric and magnetic field. And yes, they are perpendicular, as I said, yes, they are normal to each other and also perpendicular to the direction of the magnetic field. So these are the physical degrees of freedoms of or polarizations, these possibilities. And these one can also equivalently express as E plus minus the circular. So these are the linear polarizations, or we can have the circular polarizations. So E1 plus minus. And these, from the fact that they are perpendicular to the direction of propagation, obey this kind of equation. And also, if we think of them as, yes, four vectors now, not just as three vectors, we have that they are let me write down what I write and let what I have. Okay, so this is obviously if you conjugate them, you get the other part of the polarization. Good. And then you also have plus dot E minus equals minus 1. Okay. So yes, all right. So these relations come from the fact that these two vectors are normal into each other, and then the fact that you have packaged them in this combination. So let's say E1 squared in the four-dimensional signature we have would be minus 1. E1 dot E2 would be 0 because they are perpendicular into each other. And if we just package them like this and use the fact that A1 dot A1 equals, sorry, let me write A1 AI squared equals minus 1 because this is a spatial component, and then A1 dot, sorry, E1 dot E2 equals 0 because they are perpendicular, and you end up in these conditions of the polarizations. But if you want to convince yourself, this is a small exercise for students, which I will denote by the acronym EFS from now on. All right, if you want to, like, yes, brush up, yes, a little bit of this, your calculation skills and convince yourselves. So, okay, how are we doing on time? Wow, it's almost an hour. Shall I make a stop now or maybe in 10 minutes? I wanted to just put interactions in and then, yeah, if can you bear another 10 minutes or, okay, cool. Let's end then the review of QFT. I hope I did not bore you, but it's good to maybe make contact with some notions that we will be using. That's why I started gently and I wasn't sure about the level. All right, so adding interactions, the last bit, which I will try to cover relatively quickly, 10 minutes or so. So interactions. I think this is, yes. So The EOF we looked at, let's say for G equals 0, just to also include the non-abelian gauge field, are linear equations. And linear equations means superposition. Particles just move on straight lines and don't talk to each other. Linear equations means no interactions. No one talks to anyone. So how do we introduce interactions in, yes, classical or quantum yes, systems? Some source, yes, that's possible. Some external, yes, if you want some external field on them, that's good. But in this notion, just to have the fields interact with themselves, exactly. So interactions means nonlinear terms, simply. Nonlinear terms in L. That's all we need to do. Just add some piece, which is no longer, well, linear, I should say, quadratic in the, yes, Lagrangian gives linear equation. So beyond quadratic is the right way to say it, let's say for the Lagrangian. So yes, and we have, let's say for the, like, for the phi to the fourth theory, you have Klein-Gordon plus some lambda, let's say, and then some phi to the fourth piece. This makes the equation nonlinear. It adds interaction. It means particles talk to each other. And then similarly in QED, just to talk about one gauge, to be concrete, U1 gauge theory, and then you have the two fields that are the electromagnetic field and the Dirac spinor, and then you add also some piece which is nu psi alpha mu. So again, third order piece in the fields, something non-linear. And well, it doesn't have to do with quantum field theory and quantum mechanics per se. When you have, yes, nonlinear equations of motion, you most likely cannot solve them exactly. There are, of course, notable exceptions like integrable systems that many people here have expertise, but let's say random interaction that you will put in over there will most likely not be able, you will not be able to solve even the classical equation of motion exactly, let alone to try to quantize and, yes, describe a system quantum mechanically. So what do we do in this case? We have to take a step back and make some assumptions. And so instead we assume that we have some particles that are initially free. So t equals minus infinity, you have some free particles that are described, let's say, by linear equations. Okay, they might self-interact in some way, but okay, let's think about the interaction between them, not with themselves. And then there is some interaction region where you have lambda or g to be small. You can't have two large interactions, otherwise this region will also most likely extend off to infinity, and you will not be able to make this kind of assumption and approximation. So this is time advancing here. And then you also, you don't look, you prepare some particles that you know in the far past, and then You let them do their thing and talk to each other when you're not looking, when you're looking elsewhere, and then in the end, you go, when they have moved away from this region and they are again free, and you try to measure and see what comes out. So this is the in state, incoming state, and this is the out state. And because the particles interacted, the state, so it's the same type of space, left and right, but interactions have rotated a state. Uh, the one you end up with is no longer the same. It's some kind of linear combination of these and other states. And so what we do is we compute the S matrix. Namely this kind of overlap. And you do this perturbatively. Meaning as an expansion in lambda and g. And then you at least have some control. You are able to get approximate solutions and improve on them. And of course, in the quantum world, we never talk about certainty. Everything is probability. The initial state evolves into a different state. Sorry. So you started with two gluons, you ended up with a gluon and a Higgs looking at in some other direction. So this is really what is measured in experiments, is probability. You send out hundreds of particles, hundreds of protons and protons, and they're, in fact, they're constituent gluons and the quarks that smash against each other. And you know what you prepared beforehand. This you have control over, at least to a great extent. And then you look outside and you make the experiment 100 times and you see 20 times there are two gluons and nothing else in this direction. 30 times, three gluons in another direction. 5 times Higgs plus gluon, and so on. So this is the main quantity, and you also have some at least approximate way to get it. And in fact, so more specifically, you only care about, you single out interacting part. Single out interacting part. Because it is also possible that particles do not talk to each other. So you let, as you separate out, nothing happens. The end state is the same as the initial state, and then you also include the interacting bit. And so it's there for this bit out t out equals to pi. Okay, some conventions, some normalizations. Of course, the total momenta before and after, we have momentum conservation. This needs to be conserved. It's a conservation law, and then you have what is called a scattering amplitude. And this and its building blocks is what we are after in this course and yes, in the length of this and the following series. Any questions? If not, I think it's a good time to take a break, right? Just an hour, yes? Yes. Mm-hmm. No, in the end, you get always something colorless. That's true because you don't have, yes, everything needs to be. Well, FADEF and yes, the School of Leningrad started the gravability with the hope to understand something about non-perturbative quantum field theory in general. And it's an impressive yes, line of work that just has so beautiful yes, overlaps with other areas also of physics and mathematics, but nature is not integrable, at least at least yes. Mm. So, of course, I was very indeed, I skipped this detail for the sake of simplicity. This is what happens in the so-called hard scattering. So, because of asymptotic freedom, when gluons and yes, strongly interacting particles are at very high energies, they act almost as free, or it's possible to use perturbation theory there. So it's the opposite of our normal intuition. You have to be at high energies for the particles to interact weakly with the strong force, and then you can use perturbation theory. And once you do these calculations about the hard scattering, when the constituents of protons come into each other, then you have numerics. You have to rely on yes, programs and models that do the hadronization. They take these like colored particles and describe how these emit radiation and other particles and form jets. And in the end, what you measure are the standard yes, fermions, the standard matter that you see in the standard model. But yes, this is something that I will not be touching on. These Pythia and all these, yes, Lund models about how the hadronization process works. So that's the very, like, we can also discuss the two of us, but for this audience, I think that's an appropriate answer. And Mhm. For the sake of this, yes, lecture series indeed, and yes, I will be talking about the partonic, yes, cross-section or partonic S-matrix, and then there are theorems that tell you that you can factorize what happens in the hard scattering and what happens with hadronization. Otherwise, it wouldn't work. There's a theorem that tells you the total cross-section of what you actually measure in experiments is the partonic cross-sections multiplied by the parton distribution functions. And then you can describe what is really the probability that you measure. This is the theorem of Soper, Collins, Soper, Sterman, this factorization theorem that gives you then the actual measurable quantity. All right, more questions? That's yeah. So you are talking about just. So what does arrow mean for you? Does it mean the direction of the like spatial momentum or the like changing particles to antiparticles? One needs to be careful what one means. It's the same probability. Well, these are the so-called Whiteman axioms of quantum field theory, where particles are defined as states of the Poincare group. And the Poincare group has also time reversal and parity symmetry. So, okay, the Lorentz, Poincare is Lorentz plus translations. The Lorentz also includes the full Lorentz group, not just the orthochronous part, not just the like component near the identity, also includes time reversal and parity. And therefore, what you are asking, yes, will also be the same probability. Part of this, yes, it's part of, yes, how, well, you're welcome. Well, we can stretch out a bit and do come also in person if you want to discuss, yes, if you have questions that you would like to discuss in private. And let's resume in 10 minutes or 5. Let's say 5 because we also had a discussion. Okay, so let's resume because time flew. We just have, what, 40 minutes left. So let's then, after this introduction, let's move on to discuss what scattering amplitudes depend. So scattering amplitudes, they are some quantities, they have some variables, they have some quantum numbers related to the particles they describe. So what are these? So 1.3. What do scattering amplitudes depend on? Okay, who will tell me from what we discussed so far, what we know? Yes? STU, so Mandelstam invariant. So, okay, very good. So 1.3, 1 kinematics. Very good. So each particle uh, has momentum, comes with a momentum I mu. So particle I. And then if we have for n particles in 4 dimensions, we have the number of independent kinematic variables. Just let's do some simple counting. Is what? Who was the raising? Okay, for n, very good. For n, and then minus 4. Okay, so these are the number of pi. And what is this? Momentum conservation. Very good. Very good. Is that all? Energy and momentum, that's why it's 4. Yes. Is that all? That's internal constraint. This has to do with, yes, how loop momenta are related, let's say, to. What's that? On shell, well, you mean, okay, this also includes p squared. So, okay, yes, you can also include them there if you want. Anything else? They are symmetries, yes. So what are the symmetry transformations of momenta? Sorry? Lorentz symmetry. Lorentz symmetry. Okay, how big is the Lorentz group? It has 3 rotations. Rotations are included, and also 3 boosts. So it's 6. And this means that we can pick a reference frame that is convenient for us and set some of the momenta to 0. For example, we can go to a rest frame of a particle, and then we can pick one axis where one of the other particles is coming, and then a second axis when a second particle is coming. So we can use the symmetries of the Lorentz group. So this is Lorentz. To get 4n minus 10 different kinematic invariants. And here, in these lectures, here we will focus on massless particles. So this means we will take pi square equals 0 for all I. And there are how many variables we will have? The little group, yes, but now we are very good. So in this case, the number of dependent groups of sorry, 4n. You're welcome to correct me when I do typos. So is then 4n minus n minus 10 equals 3n minus 10. So for example, n equals 4, we have 2 Mandelstam invariants, and these are the usual SLT. These are the standard SNT Mandelstam invariants. If you have n equals 5, you get 5. And if you have n equals 6, you have 8, for example, just to put some numbers there. And then, okay, that's the total number of independent variables. But nevertheless, we usually want to write things in a Lorentz invariant way. Okay, so express in Lorentz and for this, we can consider the Mandelstam invariants, the usual. Or equivalently, we can consider products, scalar products, so products, pi dot pj equals 1 to n. So because simply if you take this and square it, you will get a sum of products. That's why the two are different choices of linear basis, let's say. So how many do we have? How many distinct Lorentz invariant quantities do we have? So we can pick I and J any way we like. Yes. Yes. So n choose 2. Very good. So of distinct, let's say, invariants. Invariant is then n choose 2. And then we are also uh, thinking about massless particles. Okay. So minus n, again, massless. So this is a half n times n minus 1 minus n equals half n times n minus 3. So two different countings. No, the 10 is the momentum conservation of the Lorentz. Yes, yes. No, because momentum conservation tells you that P4 squared is P1 plus P2 plus Pn minus 1 squared. And even though each of those P's may individually be more, light, the sum is generally not. Any number of? This would change. I'm subtracting this. I'm assuming now, so if P squared equals 0, I don't count it. Yes. I'm including also the external masses in this count in general, if they exist. So you are asking, you would like to separate and count all masses differently and all momenta differently. Is that the way? Is that the reason? It's a variable of your amplitude. Does your amplitude depend on the mass of the particle? All right. So the thing is that this number is different from this one. So what's going on? So let's see, n equals 4, you get again 2. All right, so nothing changes here. N equals 5, you get again 5 if you do it on the spot. And if you do n equals 6, what will you get? Who will tell me? Nine. So these things don't agree. What's going on? The answer to this is that they are not all independent. They are not all algebraically independent. And so they are not all independent. And how can one understand this? One can understand this uh, because in d dimensions, there exist at most d independent vectors. This means that if I pick them, let's say, pick as P1 to P4, and any other vector, Pi, will be a sum Pj. Yes, from 1 to 4. Yes. That's because U is in fact dependent. U is related to St and the mass of the particle. That's why. Yes. Mhm. So already in this counting, I was looking at, let's say, Mandelstam invariants that are unrelated by linear relations. This is a linear relation. U is m squared. Yes. So I'm already dropping linear relations there, and this I have taken into account. So the fact that we can write any vector so any 5 vectors in 4 dimensions are necessarily linearly independent. This is what this tells you, and therefore you can. Uh, um, this implies, so defining this matrix G of Q1 to Qm to be the determinant, sorry, not the matrix, the determinant of Q1 dot Q1, Q1 dot Q2, Q1 dot Qm, and then all the way to Qm dot Q1, Qm dot Qm. Then you can know that implies G P1 dot 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 P4 Pi equals 0. So, and this is a good exercise for students. So, exercise to convince yourselves. But when is the determinant of the matrix 0? When some of the columns are linear combinations of the rest. So this is how you essentially show it. You take Q1 to Q4 to be your P's. You take your Pi, so I is greater than 4. Yes. And then you show that this column is a linear combination of the rest, essentially. And this is a quadratic relation. So quadratic with respect to the Mandelstam invariants. Okay, if it's just 5 particles as here, we essentially have one relation. So this counting counts distinct Lorentz invariants, but they're not all algebraically independent. Only a subset thereof is. And then if you want to write your amplitude or your function as with respect to just independent variables, solving these quadratic equations is a mess. So it's some huge polynomial expression that is up to quadratic in the Mandel sums of the scalar products, and this just becomes, if you, okay, you know the solution to a quadratic equation, but the solution looks so ugly that your expressions grow, and you cannot also, usually you cannot, if you have square roots, necessarily. Square roots obscure the structure of your function. So therefore, we need better variables. Before I go on, let me pause. Is it clear why we run into problems here? We just want to describe our functions, our amplitudes in terms of Lorentz invariance. Why? Because we want things to not depend on the frame that we are at. But if we try to do so, not all of these are independent. Now, if you leave them as such, then you cannot simplify your expressions because not all of them are independent. You might have some huge mess that cancels to zero because you have not replaced, you don't have just independent variables. If you try to use just independent variables, you run into huge expressions, and then dealing with products of different square roots, just like you better give up. It's very, very tricky. It's not as if you had rational functions. So we need better variables. That's the essence. Okay, and these countings are good in general, whatever physical quantity you describe in quantum field theory. It's good to know, good exercise in gymnastics in combinatorics and counting. So since I just have 20 minutes left, let me briefly mention what two other things we need. We need also, sorry, this is 2. Yes, spin. So particles come with spin, as we discussed, and we talked about also the vectors and the polarization vectors and the also polarization spinors for Dirac particles. And in fact, for massless particles, you can use helicity. So essentially, when you are talking about spin, you remember from your SU2 representations that you have one label for the total spin, like the eigenvalue of the whole representation, and then different representations, different states. So you can have different states in the representations that are labeled by projection of the spin on some axis, say the z-axis. So the question is, all right, now we have particles with spin, which axis should we use to project our particles? And we know the spin, total spin is 0 for scalar particles, half like the Casimir, the value of the Casimir, the J, so-called the J eigenvalue is 0, a half, and 1 for scalars, fermions, and gauge fields. But how about the other quantum number? How do we distinguish states within which are all of spin half or spin 0? And so for massless particles, okay. So let me define helicity. H is the projection of spin on the direction of momentum. And why does it make sense to choose this kind of projection of spin, or this axis, to like also describe the projection of the particle spin? Very good, very good, excellent. So what your colleague said is that if your particle were massive, you could make a boost such that the direction of your momentum would change, might go in the other direction. So it's not a Lorentz invariant. Helicity is not Lorentz invariant if you have masses. So this is Lorentz invariant for massless particles. And something that relates to what I mentioned about the QFT review earlier is the only allowed values. This has to do with the representation theory. Allowed values of spin S are plus and minus S. So normally, if you have a massive particle, you know that the projection of the spin can be from minus S all the way to S. But for massless particles, you have this simplification. And only 2 out of these states survive. And I won't have the time to give you a fully fledged argument on this, but okay. For spins half, that's all you get. So for Dirac fermions, no problem, no question. For gauge fields, which I'm focusing on, we already saw that there are 2 physical polarizations and not 3. So this is, yes, a consequence of the masslessness and of gauge invariance, that in the end you get just 2 different projections. So particles, massless particles, their yes, scattering amplitudes also depend on helicities, on spin, on helicity. And finally, what else? Who will tell me? Any clues? Yes? Charge? Color. Very good. Color charge. So if you have it, because you have, yes. So for gauge fields, for gauge, for A mu and particles interacting with them, also have color charges. For example, you have, I skipped this part for today, but okay, we all have seen Feynman diagrams. Sorry, let me do the 3 particle vertex. So this depends, this is proportional to FABC, where I'm considering, yes, 3 different gauge fields, one with an index A. So let me just say that, yes, TA, TB. So the F is a structure constant, is again proportional to FABC, TC. And this index is, I wrote it before, let me write again, is A mu A T A. So essentially, since the gauge field is a matrix, it comes with a generator. There are several of them, each like gluon, therefore comes with a certain generator. Its interaction comes with the structure constant. This is yet another variable that we need to keep track of. So these are the variables of our function scattering amplitudes. And now I will, now that I have summarized this, I can pause for questions. Good. And then for the last 15 minutes or so, let me at least start with introducing spin or helicity variables. So some hopefully new pieces for most of you. So I already motivated why we need better variables than just Mandelstam invariants. And these variables, they describe both momenta and helicities. So you kill two birds in one stone. You can describe both different quantum numbers or particle, variables. And also they have the feature that they automatically satisfy momentum, the masslessness condition, and also the polarization conditions for conditions. Such as P slash U equals 0. So this we covered when I reviewed quantum field, QFT for you. We wrote it for the general case of massive particles. When you do the Fourier transform to solve the Dirac equation, this is how it reduces to when we have massless particles. Still, if we are to describe particle polarizations, we have to find U's that satisfy this equation. So these types of variables automatically fulfill these constraints, these conditions that our variables will have. So we start to define these variables. We start by rewriting the momentum of the particle mu as a matrix. Alpha dot alpha equal sigma bar alpha dot alpha mu dot p mu, where sigma bar mu is just the three different Pauli matrices and also the unit matrix. So these are Pauli matrices. So, okay, I take the Pauli matrices, I write the row index as alpha dot, the column index as alpha, that's notation, convenient or not, and then this is, I multiply essentially the momentum with the three Pauli matrices and also the identity, since we have also a temporal component. So that's all I do here, and if you use the standard definition of Pauli matrices, you see that 1 plus 2 minus I, sorry, minus 2. So, okay, maybe the indices look funny, but really, I'm just taking P0 and I multiply it with the identity, P0, P0. I take P3 and I multiply it with sigma 3, so minus 1, 1, and so on. Nothing scary here. And then it's, so in this way, sorry, maybe I should not use this side of the board. So by doing this rewriting, we can see that P squared equals 0 translates to what? Very good. And so we have a 2 by 2 matrix that has determinant 0. What does this tell us about the form of this matrix? Keep this. What's that? Yes, yes, indeed, the two columns or the two rows are dependent. So how can we write it if we have a 2 by 2 matrix where the one column is proportional to the other, or the one column is, or one row is proportional to the other? Yes, very good, very good. So therefore, P alpha dot alpha equals lambda alpha dot lambda alpha. Clearly, you see that if you take a determinant of this, it's 1, 1, 1 dot 1 times 2 dot 2 minus 1 dot 2 times 2 dot 1, so it's 0. But it also goes the other way around. It's really just to give you, it was said already, but to be even more concrete. We can have, let's say, 1, 3, 2, 6 is really 1, 2, 1, 3. That's all it's telling us. So, okay. No, sorry, I should have written tilde. Yes. So it's a product of two vectors. And this is, yes, very, very useful realization because, okay, in fact, this is useful, but it also tells us, okay, we did it, you know, with some gymnastics and some things that might look as if I took them out of the hat. Sorry, something is wrong with scrolling. But this is really, this is a realization of local isomorphism, of the local isomorphism of the Lorentz group. SO 3, 1 is locally isomorphic to SL2C cross SL2 copies of SL2C. And SL2C, if you have not run into it before, this is a complexified SU2. So it has the same type of commutation relations. It's just that the generators are not Hermitian. and so on. That's all it tells us. So essentially, you have some vector on the left. So you have an S of 3, 1 vector. And then on the right hand side, you have an SL2C spinor squared. So left and right. So two different copies of this smaller Lie group that is roughly like SU2. So its fundamental representation, its spinor, is a two-component object like SU2, spin up, spin down. So these are what these lambda tildes and lambdas are. And we just make sure we tilde them and put the dots to make sure we're not confused which of the two factors, since it's the same group, which of the two factors we are talking about, and we don't mistakenly multiply one with tensors of the other and so on. And also, one explicit realization, choice we can make. Let's again be explicit, so to demystify everything. Let's take lambda tilde alpha dot to be 1 over P0 minus P3, P0 minus P3, minus P1 minus I P2. And let's take lambda, sorry, this should be lambda alpha, I'm sorry. Lambda tilde alpha dot to be the same prefactor, P0 minus P3, and then P0 minus P3 minus P1 plus I P2. So this is really the same as this example here, so to speak. If you multiply this, like this is a column vector, this is a row vector, sorry, yes, this is a column vector, this is a row vector, you obtain this matrix over here. And, okay. You can recover, let's call this box. To convince yourself. I mean, one can see it by the eye, but just to practice a little bit. And let's see. Do I have 3 more minutes? Good. All right. So just to not to finish off, yes, let's say abruptly, and maybe I sped up a little bit, but still tried to motivate and give some background on all the formulas I wrote. So I wrote a particular realization, but note that not unique. That okay is invariant. Well, no, sorry, not this equation. This equation. So let's call this. I'm glad that I still have it here. Under, does one see it? So if I just multiply lambda with some complex number, how can I offset this so that this equation remains invariant? So essentially, I have the freedom to shift things around from one side and the other. And this is essentially why we can also describe not just momentum, but helicities also. Helicities have to do with phases of scattering amplitudes. And so just to give you the basic invariants that we can build, and okay, I will really write down this side of the blackboard and this one, and then we're done. So so since we are in SU2, you remember SUN groups have also Levi-Civita tensors that are invariant tensors from your group theory course. So by invariant SL to C invariant Levi-Civita. So we have lambda alpha equals epsilon alpha beta lambda beta. And then similarly, lambda tilde alpha dot, so lowercase, is we're again to be concrete. 1, 2 is 1 bar 2 dot equals 1. And then the other way is minus 1. And furthermore, okay, so I wrote both, good. And then, since we have this invariant tensor, we can also define scalar products. SL2C, define SL2C, scalar products. Ij is lambda I alpha lambda j alpha, and similarly for the dotted. So Ij, but now we have the indices in a different order. This has to do with keeping all the minus signs, keeping track of the minus signs. So alpha dot j, where you have here, this is the northwest, so northwest, southeast, whereas this is the southwest, northeast, meaning the order. This is okay. Maybe there's nothing deep to it. It's just a formalism that allows you to do calculations and keep track of all the signs. And then from this, then you may want to prove this. Sij, yes, I defined this already. Sij, to connect to the usual Mandelstam we talked about, is Ij bracket Ji. So the usual Mandelstam invariants we defined. So if you want this SL2C scalar products, they are square roots of Mandelstam invariants, so to speak. If you multiply them together, you get the Mandelstam invariants. If you leave them, they also include the phase. They have also additional phase information, that you can then assign to helicity, and this we will cover in the next lecture. Yes? Yes. Yes, thank you. Yes, dotted indices and tildes always go together, indeed. But already now we can go back to the so-called Park-Taylor formula that I wrote to you at the beginning of the section, and we can at least understand, if not the whole formula, definitely the right-hand side. It had these kinds of SL2C products in it. So if you need to keep something from today's lecture, is that similarly to how physicists in the Middle Ages and philosophers and mathematicians had to do a change of reference frame and put the sun in the center of the planetary system to be able to tell the orbits that we were seeing in the sky, the complicated orbits. Similarly, here you have to pick the right set of variables. You pick your right coordinate frame, in this case, these spinor variables, instead of Mandelstam variables for your kinematics and helicity spinors, in order to, helicities, in order to be able to illustrate and reveal some simplicity.
And those spinors, they're bottoms.
They are, yes, they are indeed the commuting spinors. SL2C spinors, they are commuting spinors like the SU2 spinors. Very good. Mm-hmm. Indeed, yes, these are non-compact, yes, this is a non-compact group. It still has, so compact groups have both lowest and highest weights. Namely, they can be created and annihilated. These types of non-compact groups, they have, let's say, mild non-compactness. They still have a, let's say, lower weight state that you annihilate, but then you can keep creating and creating ad infinitum, roughly speaking. But yes, you can still have also the compact representation. So you can have these, you can have also the compact SU2 representations, no problem.